Hello and welcome to this episode of the Industrial Engineering Notebook. Today's topic is defining integrals. This is a really important math thing to have in your toolbox. It comes up over and over again in a lot of different engineering equations, and if you don't understand it, you'll get lost real quick. So first thing we're going to do is we're going to recall the derivative. Remember that guy from way back when? Maybe you watched the video on it. If you have a function and you want to know the rate of change or the slope, you pick 2 points on the function and then you do the rise over the run. Maybe that's a rise of 2 and a run of 3. So then your slope would be 2 over 3. And because it's a straight line, that slope would be the same no matter what 2 points on this line that you picked. So the graph of the derivative would look like this. And taking the derivative of this equation would give you this equation. So derivative goes this direction. We also talked about how for functions that are a little bit more curvy, you can't just pick any 2 points on this curve because you'll get all kinds of different rises over runs. So what you need to do is pick 2 points that are right next to each other, draw that tangent line, and then do the slope of the tangent line instead. And if you plotted the slopes of all those tangent lines, you'd get something that looks like this for the graph of the derivative. And again, we're going from function to derivative. But integrals, we want to do something different. For an integral, we want to go from the derivative back to this function. So we want to be able to go backwards. So let's look at an example. Let's say you're driving a car and you are a safe driver who goes the same speed. You're going straight in one direction, the same speed at 60 miles per hour. And the hours go by and you're still going the same exact speed. 1 hour, 2 hour, 3 hour, 4 hours. And over here, we're going to plot the distance traveled at each time. Okay, at hour 1, how many miles have you traveled? Looking back over here, 60 miles per hour, you do 60 miles per hour for 1 hour, you've gone, that's right, 60 miles. So 60 miles right here, and this is all assuming that at time 0, you haven't traveled any miles. You've traveled exactly 0 miles. If you had already traveled 300 miles at time 0, then it would be 60 plus 300, 360. But you know that because you're smart. Next hour, what is the total distance traveled? 1 more hour at 60 miles per hour means 60 more miles. So you've already gone 60 miles, add 60 on top of that, and we got 120 miles. And at this point, you can see where this is going. You get these 4 points, and it turns out if you plotted every single point, you'd get a straight line that looks like this. Pretend I hit all those points. And just like that, we've gone backwards from the derivative. Remember how we went from this f of x, this straight green line, and then we went to this derivative? Well, we just went backwards here. We started with this straight line, which was a derivative. It was a rate of change, a speed, and then we went to distance traveled. And like the derivative, it's easy when you start with a nice straight line, but it gets tougher when you have a curvy line. What if you're a maniac who drives like this? And to answer this question, we need to go back and really analyze what we did here. It's almost like we took the area of these rectangles and added them up. And it's almost like we were plotting the area under this curve. In fact, it's not almost like that. That's exactly what happened. That's the magic of the integral. One way to look at this graph is as an accumulation of the area under this curve as time goes on. I made it easy and put time in these 1 hour blocks, so it was easier to do the math on the area of each of these blocks. But it could have been any unit of time. It could have been a really large unit of time or a really small unit of time, and it wouldn't have mattered for this nice, easy, flat line. But we want to find the area under this curvy line. And we can try these 1 hour blocks, but we're running into a problem here. And that's that we're not really getting all of the area under the curve. We're missing out on some parts. How do we fill in those spots? And the trick is not to use these big blocks of time. We want to shrink them as small as possible. So that way we have these rectangles, these itty bitty rectangles, and then here's the next itty bitty, it's not itty bitty, it's just really, really slim. And you see they're so close together that that area almost doesn't exist. That area that we're not accounting for right there almost doesn't exist. So what amount of time is this? Maybe a second or a millisecond. But we would call this, if time is the variable t, we would call this dt. This just means a little bit of change in time. 1 sliver of time, as small as sliver as you can get. I hope that was enough S's for you. And maybe speed, maybe that's f prime of t. And one of those little slivers, let's see how we're going to calculate the area of that little sliver. It would just be dt times, well, whatever f prime of t is right there. So f prime of t right here, because that would be this point on the function, so that would be the height of your little sliver. So what we're doing over and over again is we're doing f prime of t times dt plus another f prime of t times dt plus another one, and so on, from t equals 0 to t equals 4. And this is a sum. And now what we need is a more concise way to write this, because that's a mouthful, or a page full, or whatever. And now we have our definition of an integral. F of t is the function we want to get back to, and it is equal to the sum, this is a really skinny s, sum of the f prime of t times dt from t equals 0 to t equals 4. And it didn't have to be 0 and 4. It could have been negative 2 to 6. Or it could have been negative infinity to 5. Or it could have been negative infinity to positive infinity. Or 3 to positive infinity, or whatever. So let's just say from t equals a to t equals b. And knowing this equation is a really big deal. Obviously, we can't, for every function, make those little slivers and add them up. That'd be way too hard. Practically impossible. So we need some math formulas that will just automatically tell us what f of t is. When we see this notation, we can just plug whatever f prime of t is into some equations, and it'll spit out f of t. And I'll explain all that in the integral rules video, which will be coming up. If you like this video, please hit the like button. If you want to see more videos like this, please hit the subscribe button. And if you have questions, please put them in the comments. I will try to answer them.